Great. Welcome, everyone, uh, to today. You made it. Um, Before we get into proper lecture content, I wanted to bring to everyone's attention a change I made to the project um, a few minutes ago. I sent out an announcement over Canvas, but I just wanted to point out here that the budget in 4.2 it should now be 3.6 million. It was 1.8 billion, and as it turns out, that is just way more than is needed uh, to do this problem. And so, in an effort to make the solution interesting, I've dropped it down to 3.6 million. This shouldn't change your model very much. You should just be dropping in, swapping out a coefficient in the constraints. So hopefully that's not too much of a hassle to change if you've already worked on this part of the problem. But the new version is the one that's on Canvas at the moment. So good. Okay, so let's get into the course proper. That's the wrong button. I want to press this button. Okay. Duality. So what we've done so far in this course is model problems as linear programs, implement those models in software, and solve models by hand with the simplex algorithm. Um, so those are big and important, but this content is, I think, the most interesting part of the course because it has huge implications for all sorts of mathematical problems, nonlinear programs, integer programming, all sorts of things. The book, if you read 3.1 or 3.2, the book talks about forming intuitive bounds on an LP, and that intuitive may not be what you thought of the process. Am I coming through now? Good. Okay. Pardon me, my headphone battery ran out. Should have checked that before class. So, you may not have found uh, the content and the reading quite as intuitive as the book claims that it is, but we're going to try today to sort of generalize that process and also talk about how it works in a way that is hopefully makes a little more sense. If you didn't quite catch what the book was laying down. So, suppose we have this linear program. This is the same LP we worked on yesterday. We added a constraint to it to get us a degenerate solution. But here I've swapped out the y's for x 2's because we will be using y as our dual variable, and I don't want to get us confused. So we want to try to find an upper bound to this problem. And if you remember back back a ways, the book did an interesting thing similar to the dual. It tried to show a contradiction in the constraints by taking linear combinations of the constraints and showing that they contradicted one another in order to show that an LP was infeasible. So the book proved infeasibility by taking linear combinations of the constraints. This one, of course, is not infeasible. We can see the feasible region right there. So we're not going to do exactly that, but the process is sort of similar to when the book did that. I don't remember exactly where that happened in the book. But we can see graphically that since this is a maximization problem, we can see that the optimal solution to this problem is this extreme point, which happens to be 2.24 and has a objective function value of 14. So remember that that this whole LP is 14, or the objective function is 14. So, like I said, the book took linear combinations of constraints. And so we're going to do something, we're going to do the same thing, but we're going to use it to show a different sort of idea. So let's take some linear combinations of the constraints. A linear combination, if you don't know, or if you need a refresher, is simply the addition of two things with some coefficients. So here, say our constraints are linear combinations of x1 and x2. So basically it's just a linear function where the variables are. In our case, what we're about to do, the variables, that's maybe a bad way to say it, are the constraints themselves. So what we're going to do is multiply all of these constraints by a coefficient. In this case, I want to pick 3, 0, and 8. And then we're going to add them together. So plus all of this. And that's going to give us this inequality. 3, 0, 8, 3, 0, 8. So here we've just added up the left-hand side. And since all of these are less than or equal to equations or constraints, we have a less than or equal to here. The right-hand sides sum together. And this reduces to 3x1 minus 6x2 plus 8x2 less than or equal to 3 plus 32. Which then simplifies further. 3x1 plus 2x2 less than or equal to 35. So the first thing we need to notice is that this term is the same as our objective function. And what that means is that our objective function is actually bounded. It has to be less than or equal to 35. So I just pulled these numbers out of the ether. I picked them so that we would have this equality. But we're gonna come up with a systematic way to find these numbers shortly. So first, I want to convince you that this actually works. This actually is a bound on the whole LP. So row operations are just linear combinations of the rows. So when we're doing row operations, we're taking linear combinations of the rows of an augmented matrix, right? If we're talking about a system of linear equations, we do row operations to find a basic solution. And that basic solution is actually a solution to the problem, to the system of equations before we did all those row operations. It's a solution. It satisfies everything, no matter how many row operations we've done to the problem. That solution is always a solution to that system of equations. So that stems from the fact that every solution, let me put a different color. Every solution that is feasible or better yet, that satisfies a set of linear constraints. Those could be equations or inequalities or what have you. Also satisfies any linear combination of said constraints. And this was hopefully proven to you in linear algebra, or at least you were convinced of it. But the idea is that multiplying a whole constraint by a number doesn't actually change the solutions to that constraint. And similarly, adding two constraints together, it could open up more feasible, more solutions that would satisfy, but it will never cut off a solution that used to satisfy those constraints. It will never remove that satisfaction. So in other words, this linear combination so every feasible solution to the linear program satisfies this inequality. For whatever values we put in those blank spaces, as long as they're consistent across the sides. What that means is that any solution that satisfies this set of constraints also satisfies this constraint. And this constraint happens to have its left-hand side equal to our objective function. And that implies that any feasible solution has an objective function value at most 35. That feels like a long and convoluted argument. Any feasible solution satisfies any linear combination of the constraints. Our linear combination happens to put a bound on the objective function. Our left-hand side happens to equal the objective function, and because we have less than or equal to's everywhere, that objective function is less than or equal to the right-hand side of our linear combination. So let's do another example linear combination and see what shows up. See if we can make a little more sense out of this. So I'm going to pick a new linear combination. I'm going to pick 0, 1, and 1. We're going to add all of these together. So we get 0, 1, 1, 0, 1, 1. And then this reduces to 3x1 plus 2x2 is less than or equal to 10 plus 4 is 14. Which you'll remember, if we come back here, 14 is our optimal objective function value that we found for our LP. And we know that because the left-hand side of our new combination of constraints is also equal to the objective function value, that this whole LP is bounded. Its objective function value can be no bigger than 14. Which is another way of proving that the solution we found graphically, this corroborates that it's optimal, because no feasible solution can be bigger than 14. And we found a solution that is 14, so it must be optimal. So this bound equals the objective function value of the solution we identified earlier. Thus, there does not exist a feasible solution with larger objective function value. I.e., it is optimal. And we can also kind of turn that on its head. We can turn that argument around and say, hey, we actually found a solution that has objective function value of 14. That means that if we found by some sort of magic, we found a better linear combination here, a linear combination that gave us a bound of 11 or 5, we would know that linear combination, something is wrong there, that something is wrong with that bound, and it's not actually true because it contradicts a solution we found. Suppose, I guess, that we found some linear combination that gave us this equation. Well, the problem is we found a solution 2, 4 that equals 14, which contradicts our bound. Fortunately, we haven't found a solution or a linear combination that gives us that, so we don't have that problem. What I'm saying is this linear combination is the best we could have found. So this linear combination is in some sort of way also optimal. So let's put a pin in that and we'll come back there in a second. So in general, though, what we want to do is find a linear combination that looks like this. I'm using y, multiplying each constraint by y and adding them together. We want to minimize this. minimize the left-hand side such that this is greater than or equal to the objective function. And this being the left-hand side. So in our case, we want 3x1 plus 2x2 to be less than or equal to this linear combination, which then tells us that our objective, 3x1 plus 2x2, is less than or equal to the right-hand side. And that sounds kind of like a linear program. We want to minimize something such that something else is true. So let's think about that. Well, we want to minimize the right-hand side. Minimize the right-hand side is y1 plus 10y2 plus 4y3. And our constraints were such that this value was less than or equal to 3x1, 2x2. Now we can't compare. Oh, there should be an x2 here. We can't compare unlike terms. So we can't compare x1 to x2. So that means we can actually split this apart. We're going to evaluate this inequality term-wise. So we're going to say that this term, the x1 term, has to be less than or equal to 3. And this term, the x2 term, has to be less than or equal to 2. Correction. They need to be greater than or equal to. Was that your question, Kelly? Good. Good catch. Let's not deal with the non-negativity constraints just yet. They're a little complicated. But what we have here is a new and distinct linear program. The solution to this should give us the tightest possible upper bound on our original LP. Correction, it'll give us the tightest upper bound that we could get from this sort of process. And as it turns out, with linear programs, that actually is the tightest upper bound possible. Spoiler alert for tomorrow's lecture. This process gives us the optimal objective function value every time. for linear programs. That doesn't always extend to nonlinear or integer programs. But that's a topic for DOR2, so I'm going to skip past that. So in general, let's generalize this a little bit more. Let's generalize our original LP. Actually, before we go there, we call the original LP the primal problem, and we call this sort of upper bounding problem, we call that the dual. The dual problem. So I'll be using that term, primal and dual, plenty. So let's suppose we have this primal problem. This is just a slight generalization of what we just did. What does the dual look like here? I duplicated this slide, didn't I? I have it twice. Let's use this one. A little extra space. Well, we want our right-hand side, we want to minimize the right-hand side. So that becomes our new objective function. While keeping the left-hand side greater than c1x1 plus c2x2, greater than or equal to. So that's what we want to do, and that gives us this dual. There's our objective function. And the terms from the linear combination. So what I want us to see here is that we've swapped the position of C and B, the vectors C and B, and the matrix A has been transposed. So this row, this constraint, this row of A is now a column of A. So the rows have become columns. And similarly, the columns, A11, A11, 21, 21, 31, 31, the columns have become rows. So, more generally, if this is our primal, then this is our dual. Swap the places of C and B, transpose A, and some new vector of variables of the appropriate size to make those equations make any sense. So if we had n variables and m constraints, then here, let me do that better. Then the dual will have m variables and n constraints. In fact, each dual variable corresponds to one of the constraints from the primal problem. And we can that makes some sense when we think back and remember where this came from. We were taking linear combinations of the constraints. We're multiplying each constraint by a dual variable and then adding them together. So each dual variable corresponds to one of the constraints. And again here, this is not quite gospel because we haven't dealt with the non-negativity constraints yet. And those are going to get complicated, and that's the next thing we need to tackle. So if you're doing homework and you're trying to find the dual, don't reference this slide because it's not quite complete. But this is just what we've discovered so far. You may also notice that if we took the dual of the dual, took the dual of the dual, we're going to swap the minimize for another maximize. We're going to swap B and C again. We're going to have some new variable, Z, such that A transpose transpose Z is less than or equal to B. Wait, I forgot to C transpose Z less than or equal to B. Transpose transpose disappears, and Z will have the same dimension as X. So this is the primal. The dual of the dual is the primal. So these two problems are what's known as a primal dual pair. And this relationship will continue even when we add non-negativity to this problem. So that's important to remember. The dual of the dual is just the primal. So far, like I've said, we've ignored the domain, the non-negativity constraints, because they're a little complicated. So we have to figure this out. So let's think about it. Remember, we wanted to have this relationship. We wanted to say, this is back to our example problem, and it's dual. We wanted to have 3x1 plus 2x2 was less than or equal to y1 times the first constraint well, actually I can just write it out. x1 minus 2x2 plus y2 times 3x1 plus x2 plus y3 times x2 was less than or equal to y1 times 1, so just y1 plus 10 y2 plus 4 y3. Let me put this in. I'm going to add all those together. And the most important thing here is these two inequalities. If we do something to accidentally flip those inequalities, either one of them, suddenly we don't have a valid bound anymore. So what could happen that would negate one of those inequalities? Well, we've said that x1 and x2 have to be non-negative. So so what? Right, here we go. So if y3 was negative, suppose y3 was strictly negative, not 0, but strictly less than 0, then we're going to end up with, we get y1 times the first constraint plus y2 times the second constraint minus, or plus x2, or no. In fact, let's make this more specific. Let's make this equal -1. Then we have x2, correction, negative x2 is greater than or equal to -4. And this inequality doesn't match the inequality we want. So we could have a problem there. In fact, we will have a problem there. We can't actually add these constraints anymore because they're not compatible in a sort of sense. We can't take that linear combination anymore with any if it's not well defined. Because these, all three of these, or the first two, assuming y1 and y2 are also positive, or non-negative, they still have a less than or equal to inequality in there. And you can't just add a less than or equal to and a greater than or equal to. It doesn't work. And you may think, oh, but can't we just subtract out that -1 and be left with a less than or equal to? The answer is no, and the reasons are kind of obscure. Multiplication is not distributive in the same sort of way when you're dealing with equations rather than just polynomials or terms or inequality. It's not distributive when you're talking about inequalities rather than equations. So no, we can't just do that. What if all three of our y variables are negative? Well, then we can add them together, but we're going to get a greater than or equal to there. And suddenly it's not an upper bound anymore, and these two equations, or these two inequalities, contradict, and the term doesn't actually, the whole inequality doesn't actually mean anything anymore. Right. So what that all means is that every inequality, every less than or equal to inequality, corresponds to a variable, and if it's less than or equal to, that variable should be non-negative. So all three of our constraints here are are less than or equal to, so all three of our variables need to be greater than or equal to 0. What if, you know what, let me duplicate this page for us. Can I do that? I don't think I can do that. Dang. Okay, well, I'll just add a couple pages. Sure. So we had max 3x1 plus 2x1 x1 minus 2x2 equals 1, 3x1 plus x2 10, x2 4. Now let's swap these in our LP, in our constraints. And of course we have x1, x2, non-negative. Let me grab this fella, plunk him in here. Now, here's the thing. We still want an upper bound. And if we were to add these with positive coefficients, we would end up with a greater than or equal to here, which would give us a lower bound on our primal problem. So we still want less than or equal to in both spots, because we want an upper bound on our objective function. A 3x1 plus 2x2. Good catch. So then, remember that Uh, yeah, so if we had if these were all non-negative, then we have a greater than or equal to in all three, and we have a greater than or equal to here. If only one of them is negative, or two of them is negative and the other is positive, then we have a contradiction and we can't add them together. So they all need to be positive, or they all need to be non-positive, rather. So if we have here tells us this means that y should be non-positive instead of non-negative. And that's kind of wild that the direction of the inequality would change that much. So now, what if, let's copy all of this again one more time. And let's think about what happens if we have equality constraints. Well, no matter what yi we use, no matter what, no matter the parity or the sign on the y's, we're adding up equations. Which we can do regardless of parity. We're not going to change anything. We're not going to bungle anything up. So we get an equal sign here, no matter what y sub I is. And that means that y is free or unrestricted. It can be positive or negative or zero willy-nilly, however we want. Which is pretty cool, I guess. So, in a similar vein, what if the primal variables are unrestricted? So what if we had free primal variables? Well, from what we just remember that the dual of the dual should be the primal. That's important. So so we can kind of swap our logic in our heads and say that, well, back here the variables were free because the constraints were equations. And if we want the dual of this to equal this with free variables, then the only option is to have equality constraints. So since the dual of the dual is the primal, we can use the same logic, or we can sort of reverse the logic. To say that the equation or the constraints need to be equations. And in fact, we can do the same thing for non-negative and non-positive variables in the primal to tell us what direction our constraints should be in the dual. So, in general, we have that less than or equal to constraints imply non-negative variables. Greater than or equal to constraints imply non-positive variables. And equality constraints imply free variables, and vice versa. So any free variable in the primal will correspond to an equation in the dual, and any equation in the primal will correspond to a free variable in the dual. Which is sort of wild. So here's a handy chart. It works both ways. The chart in the book, in I think the next section we read, I think it's in 4.1, I find to be, yeah, table 4.1 in section 4.1. It has a slightly more robust version of this. Let me see. Yeah, greater than or equal to constraint is a right. So this version is for if our primal if the primal is a maximization problem. For a minimization, so we've been doing all of our logic based on the fact that we wanted to upper bound a problem. An upper bound is important for a maximization problem, but if our problem is to minimize, then having an upper bound doesn't actually tell us anything at all. So instead, for the dual, or for a minimization, get a different color. Ay, 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 achi machi. It's being obnoxious. If the primal is a minimization, we actually want to have our constraints, our inequalities point the opposite direction, because we want a lower bound rather than an upper bound. And so for that, a greater than or equal to constraint actually corresponds to a non-negative variable, and a less than or equal to constraint corresponds to a non-positive variable. Is that right? Yeah. Since we want a lower bound, so that's the dual. In general, we're going to do another example here in a second, just so we can see everything in action. Two things we need to know. The primal is the dual of the dual. And any feasible solution to the dual implies a bound on the primal. And in fact, vice versa. I'm going to prove that a little bit. The book does a similar thing. Remember, we had maximize C transpose X such that AX was less than or equal to B, and its dual was minimize B transpose Y such that A transpose Y was greater than or equal to C. So let's look at the objective function, C transpose X. Well, that's C is less than or equal to A transpose Y from our dual problem. But A transpose Y is the same as Y transpose A transpose X. Oh, correction. We need the transpose here, but not over here. And then we can redistribute things or regroup y transpose AX. AX is less than or equal to B from our primal problem. So we get y transpose B, which is the same as B transpose Y. Which is the objective function of the primal. So what this is saying is that the primal objective is less than or equal to the dual objective for any feasible x and y. So for any feasible solutions to the primal or dual, they're bounded by by each other. And of course, this is for a maximization primal. If you had a minimization, you could do very similar logic, flip the inequalities, and find the proper bound. Or you could just say that the primal is the dual of the dual, and use this result, and dualize everything one more time to swap everything around. Proof techniques, I like that stuff. So ask me about that if you're interested in a better, more robust proof of anything I've done today, because I will be ecstatic to talk about that. So I just wanted to do the dual. For some reason this page isn't loading. There we go. This is our Soylent Green problem, our best friend in the whole wide world. And this is the LP for it. So I'm going to really quick go through the dual of this, just so we have one more example of the dual. We're going to minimize. I'm not doing this off the top of my head because I don't have notes on this one. So if I do anything wrong, yell at me in the chat. So we want to minimize 1500 1500 y1 plus 20 y2 plus 100 y3 plus 30 y4 subject to. Now remember, we transpose the A matrix. So we have 1 y1, or that's actually y4. I'm doing it backwards. 25 y1 plus 0.1 y2 plus 6.3 y3 plus y4. So that was this column of constraints swapped into a, or of coefficients swapped into a row, its own constraint. Now, y4, or oh yeah, so all of our variables are greater than or equal to So if we, and this is a maximization problem, so if we come back and reference our slide, maximization problem, greater than or equal to constraints, non-positive variables. Oh, that's backwards. Maximization problem, non-negative variables gives us less than or equal to constraints. That's the one I wanted. So this is less than or equal to 0.1 over 30 is our objective coefficient here. Then the second column, 110 y1 plus 2.2 y2 plus 0.65. Oh, nope, 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 nope. Plus 1.8 y3 plus y4 should be less than or equal to 0.25 over 30. This should be our last constraint. 72 y1 plus 0.65 y2 plus 4.1 y3 plus y4 is less than or equal to 0.2 over 30. And finally, it's a maximization problem, so y1 and y2 are something, or not y2, y3. They both have the same direction. Y2 is something, and y4 is free because it has an equality there. So and these are both in relation to 0. So our y1 row is a greater than or equal to. So we come back to our chart. Maximization problem, greater than or equal to constraint, non-positive variable. So it should be non-positive, and this should be non-negative because it has the opposite, and y4 is free. And that is our dual to the Soylent Green problem. That is all the content for today. Tomorrow we're going to talk about 3 very powerful and very important, and I think very neat and very elegant results relating to the dual. The 2 theorems, weak duality and strong duality, and complementary slackness. 3 very important things that we can use to identify optimal solutions and, in fact, analyze them in some depth. So I'm going to stick around for questions, but you guys are free to go.